Over the last few lectures, we have been discussing the Lorentz transformation properties of massless particle states. Let me quickly recapitulate what we have done so far. We have talked about the little group elements corresponding to this standard momentum kappa 00 kappa, and we have found that these little group elements can be parameterized by three parameters. W alpha beta theta is S of alpha beta R of theta, and we had worked out the matrix form for S of alpha beta. R of theta, of course, is a rotation about the z-axis through an angle theta. Now, for infinitesimal transformations, where alpha, beta, and theta are infinitesimally small parameters, the corresponding operator which acts on the Hilbert space, U of W alpha beta theta, is, of course, very close to the identity, and we wrote that as identity plus I alpha A plus I beta B plus I theta J3, thus defining the generators A, B, and J3 of the little group. Now, we had also worked out the commutators of these elements, and we have seen the J3 commutator with A is IB, J3 commutator with B is minus IA, and A and B commute. Since W alpha beta theta for finite parameters is equal to S alpha beta R theta, and hence U of W alpha beta theta will be U of S alpha beta times U of R theta. Since A and B commute, you can easily show that U of S alpha beta is e to the I alpha A plus beta B, and you have to multiply that, of course, by e to the I theta J3. We had shown in the previous part of this lecture series that in order to be consistent with what we observe in the physical world, the standard form momentum for a massless particle, psi k sigma, must be an eigenstate of the operators A, B, and J3, all three together, but must correspond to eigenvalue 0 for the operators A and B. And so the only thing which distinguishes one standard form momentum from another is a label sigma, which is the eigenvalue of the operator J3. Now, because of this, UW psi k sigma is obviously to the I alpha A plus beta B times e to the I theta J3 acting on psi k sigma, and because J3 acts on psi k sigma to return sigma, the number, times psi k sigma, e to the I theta J3 just gives you e to the I theta sigma times that. E to the I alpha A plus beta B acting on psi k sigma just gives you a factor of 1, simply because A and B are both operators for which psi k sigma is an eigenvector with eigenvalue 0. And based on this, what you can immediately show is that for any Lorentz transformation lambda acting on a state psi p sigma, U lambda acting on psi p sigma is going to be, apart from a normalization factor, simply e to the power I sigma times theta of lambda p psi of lambda p comma sigma. So apart from this overall factor which comes in the front, the only thing that happens is that the momentum of the state changes from p to lambda p. The sigma label stays unchanged. That is one very important point about the way in which massless particle states transform under a Lorentz transformation. Now this theta lambda of p, of course, is nothing but the corresponding theta parameter for W lambda p, the little group element L inverse lambda p lambda L of p. At this point, let me stress one thing. Sigma is the eigenvalue of the operator J3, and we are used from non-relativistic quantum mechanics to think of eigenvalues of J3 as being half integer values, half odd integers or integers. However, that conclusion was reached in non-relativistic quantum mechanics from the algebra involving J1, J2, and J3 operators, all three together. In this context, the operators involved are actually quite different, J3, A, and B, and there is no algebraic reason whatsoever for demanding that J3 must have half integer eigenvalues. At this point, there is no reason to restrict the eigenvalues of J3 to any particular value. Because J3 is a Hermitian operator, its eigenvalues of course have to be real, but there is nothing in the algebra of the little group which prevents J3 from having continuous eigenvalues. We will see later that although algebra does not force J3 to have half-integer eigenvalues, topology of the system actually does. We are not talking about topology right now. We will discuss this in a later section. And there we will see that because of the topology of the problem, J3 will be forced to have half-integer eigenvalues. So, our familiar result from non-relativistic quantum mechanics does come back, but for a very different reason. We must now make up for one important omission. While we have given a formula which figures out the effect of a Lorentz transformation on a massless momentum eigenstate, namely this particular formula here, we do need to be able to calculate theta of lambda p for a given initial momentum p and a given Lorentz transformation. In other words, we should be able to figure out W of lambda p, from which we should be able to find out R of theta lambda p. This is of course a function of lambda and p here. Alpha and beta are also functions of lambda and p. Alpha and beta do not show up anywhere in this transformation equation, but that does not mean that they don't have any physical meaning. We will later see that alpha and beta are related to the gauge symmetry which electromagnetism or U1 particles have. Now, the one major thing that we have left out so far is a prescription for calculating L of P. So this is what we are going to correct for now. Now for a given 4 momentum P, what we need is a standard Lorentz transformation L of P, which acting on K mu gives you P mu. Remember, K mu is our standard 4 momentum kappa 0 0 kappa. When we were discussing the little group, we were only interested in Lorentz transformations which keep kappa 0 0 kappa unchanged, and there we had taken 1 0 0 1 for the standard momentum simply because an extra factor of kappa would not affect our results there at all. Now that we are actually talking about 4 momenta, we cannot really take 1 0 0 1, that would be dimensionally inconsistent. So we fix some value for kappa, doesn't matter what, but which has the right dimensions of momentum, and take the 4 momentum to be kappa 0 0 kappa. This is of course the standard 4 momentum. Now we need a prescription for the standard Lorentz transformation which takes K mu to whatever P mu we are interested in. Note that all we have to do is to get the 3 momentum of the final 4 momentum correct. Because once we have that, the energy part will automatically be equal to the magnitude of the 3 momentum, this being a massless particle. So we don't have to worry about that separately. How do we get the correct 3 momentum that we want? Note that we already have a 3 momentum of kappa in the z direction. So we can first try boosting to an appropriate parameter above the z-axis so that the final momentum gets the right magnitude p. So what we have to do is put in b of magnitude of p by kappa. This is what the boost will depend upon. And after we do that, in the new frame, what we will have is a particle whose free momentum is of the correct magnitude, but it's along the z-axis. So we need to now carry out a rotation which takes the z-axis into the direction of the final 3 momentum. And this is all that you need to do. This is not the only possible Lorentz transformation that's going to do the job for you, but this is the one we are going to take as the standard Lorentz transformation for the job. Let me point out that we have still not completely specified L of P because we need to specify exactly what R of P had to use. But before we go there, let us try to figure out what the expression for the boost B of mod P by kappa should be. Now the generic boost, when you're talking about going over to another observer with velocity minus beta along the z-axis, is given by the following. One 0 gamma beta 0 0 gamma. Of course, the sign here is different from the standard sign that you see or are used to seeing in standard textbooks, but that's basically because there you're talking about an observer whose velocity is beta. Here we are talking of an observer whose velocity is minus beta. That's just for convenience so that we are going to end up with positive numbers throughout. Now what we want to ensure is this Lorentz transformation acting on kappa 0, 0 kappa gives us our final 4 momentum. Well, not really our final 4 momentum, but a 4 momentum which has a spatial part along the z-axis but has the right magnitude. So magnitude of p vector along the z-axis, and of course being a massless particle, its energy is exactly the same as the magnitude of the spatial part. So you end up with this. All the while, remember, we are using c equals 1, which is why the velocity and beta are one and the same thing. Now, from this equation it's obvious that gamma into 1 plus beta times kappa is going to be mod of p. You can just take either the 0th row or the 3rd row of this product matrix, and that's going to give you this. So, gamma into 1 plus beta, which is also root over 1 plus beta into 1 minus beta, is equal to mod of p over kappa, something which we are going to call u, just as an abbreviation. So obviously 1 plus beta by 1 minus beta works out to be u square, and from where it's very simple algebra to show that gamma turns out to be u square plus 1 by 2u, and gamma beta, the other term in the other non-trivial term in the matrix, turns out to be u square minus 1 by 2u. So our boost for a parameter u given by mod p by kappa is given by u square plus 1 by 2u, 0, 0, u square minus 1 by 2u, 0, 1, 0, 0, 0, 0, 1, 0, u square minus 1 by 2u, 0, 0, u square plus 1 by 2u. Now, I have already said this several times before in this course of lectures, but if you're trying to compare this with Weinberg's result, you may see that the matrix is presented in a slightly different form there, but that is simply because Weinberg uses the ordering 1, 2, 3, 0 for his indices, whereas I am using the more standard version 0, 1, 2, 3. So, the rows and columns of my matrix are a bit different from the rows and columns of Weinberg's matrix, but they're essentially the same. What we have to do next is fix a prescription for this r of p hat, the rotation, which carries a unit vector in the direction of the z-axis to a unit vector in the direction of the final momentum, final 3 momentum. So this is 0, 0, 1, the unit vector along the z-axis. This has to be carried to p hat. And the easiest way to do this, at least one of the easy ways of doing this, would be to use spherical polar coordinates for this particular vector p hat. If the polar and azimuthal angles here are theta and phi, then one easy way to start from this unit vector along z and land up onto p would be the following. You could first rotate about the y-axis. Okay, let me just label the axis first. This is x, this is y, and this one is z, of course. If we were to first rotate about the y-axis through an angle theta, this unit vector would end up making an angle theta with the z-axis, but in the xz plane. After that, we have to just rotate. So first rotate about y through an angle theta. Of course, counterclockwise rotations are counted as positive. And then rotate about z through an angle phi. And this unit vector will then turn and point along p hat, which is exactly what we want. So 2 successive rotations, one through an angle theta about y, then through an angle phi about z. But there is a bit of a catch here. And the catch is the following. First of all, we must realize that the rotations that we have talked about all along here are passive rotations. There are situations where you are carrying out a transformation of the coordinate axis and the coordinates of the point change as a result of that, or the components of a vector change as a result of that. The vector itself does not really change. So basically what we are looking at is not really this. So I actually find Weinberg's description a bit confusing here. What it meant should have been something like this. You have a vector pointing along the z-axis of your original coordinate system with x, y and z-axis. Then you want to rotate your coordinate system in such a way that you end up with components of p hat which are sine theta cosine phi, sine theta sine phi and cos theta respectively. Note that the unit vector has not really changed at all. It's the components which have changed. This is what happens when you use a passive rotation. That is, you're not really rotating the objects, but just rotating the coordinate system. Remember, all our work so far has been talking about a Lorentz transformation, and rotations of course were a special case of that, where you were going from one inertial frame to another. Rotation is also just a way of going from one inertial frame to a rotated inertial frame. So all these are passive transformations. So in order to achieve that, what you really should be doing first is rotate about y through an angle theta, but not in the counterclockwise direction, but actually in the clockwise direction, so that your new axis end up pointing like this. So this is the changed z-axis, this is a changed x-axis, and you have ensured that the original vector actually makes an angle theta with the changed z-axis. Then what you would do is rotate your coordinate system about the changed z prime axis to an angle phi in the opposite direction, so the x will go back, so the y will turn as well, and now the azimuthal angle for this same old vector in the new frame will be phi. So this takes a bit of getting used to, simply because we are not actually used so much to think about the passive transformations which we are really doing. When we talk of rotations, we tend to think about actively rotating an object. This is not what is being done here. So keeping in mind that we are using passive rotations, what rp hat really should be is ry minus theta first, then you have to apply the rotation matrix rz minus phi. Notice that ry minus theta has already done the job of rotating your coordinate system, and so the next rz minus phi is actually with respect to the changed coordinate system. That's how the components change. Weinberg doesn't really explain this, at least to my mind, carefully enough. So it may become a bit confusing if you look at his next statement. In fact, he doesn't even talk about r of p hat. Rather, he talks of u of r of p hat, essentially because he wants to avoid sign ambiguities when you are talking about spin-half particle transformation laws. So he explicitly states what u of r of p hat is, and he says that u of r of p hat, the corresponding operator in Hilbert space, is exponential minus I theta j2 times exponential minus I phi j3. Let me quickly remind you that when we worked out the theory of Poincare transformations, we had seen that u of r n hat theta was actually exponential of I j vector dot n hat times theta. So basically a rotation through an angle theta about the y-axis would have been e to the I theta j2, not e to the minus I theta j2. You may have seen e to the minus I theta j2 in some textbooks, but there they are using active rotations. We are talking about passive rotations here. So this is essentially what I wanted to emphasize, basically because Weinberg sort of skims over this point, makes it seem obvious and slips you this formula, where it seems to be inconsistent with his statement earlier about this being the expression for u of r n hat theta, as well as inconsistent with the statement that he is making that you first rotate through an angle theta about y and so on. I have just stated this in some detail so that we can avoid confusion later. Indeed, Weinberg does not even specify r of p hat at all, prefers rather to give this expression for u of r of p hat with the additional constraints that theta must obviously be between 0 and pi, and phi be kept confined between 0 and less than 2 pi. The reason that he prefers stating this rather than this is the following. If you change phi, for example, by a 2 pi angle, you're essentially talking about the same rotation. So rz minus phi and rz minus phi plus 2 pi will be exactly the same, leading to the same r of p hat. But if you are acting on systems with half odd integer spin, like spin half particles, it is a minus I phi j3 will actually change sign when you add 2 pi to the angle. A 2 pi rotation indeed is not really trivial in quantum mechanics. Rather, a 4 pi rotation is, at least for spin half particles. By the way, as we have already stressed before, we have not yet proven that the sigma eigenvalue for J3 has to be 1/2 or its multiple. So far, we have no algebraic reason for believing that J3 eigenvalues are quantized. However, topology will show us later on that J3 eigenvalues are quantized to be multiples of half, so half an integer. And so this particular demand of specifying the range of phi and ending up with a unique u of r of p hat that way is actually something which makes sense. Let us now put all of this to use in actually calculating theta of lambda p for some specific kinds of Lorentz transformations and also some specific values for the 4 momentum p. And hence, figure out exactly how momentum eigenstates would transform under those particular Lorentz transformations. The calculational details tend to get a bit complicated, so I'm going to just give you a few examples where the calculation actually is not too difficult. But the basic idea can be used for every kind of Lorentz transformation with any starting momentum. Now, the first example that we are going to look at is a straightforward one. In all our examples, we are going to assume that our particle, the massless particle that we are talking about, has a momentum which is actually in the z direction. So, the 4 momentum is going to be this for all our examples. This essentially means that at least for the initial 4 momentum, L of p is simply b of u, where u is of course mod p by kappa. There is no need to rotate this momentum onto the final direction by a final rotation because the momentum is already in the z direction. So it's the boost that is all that you need. This is about the state of the system on which you're going to apply a Lorentz transformation. Now, let us consider first a case where the Lorentz transformation lambda is a boost along the z-axis through some other parameter u bar or whatever. So basically, you are looking at a particle which is traveling along the z-axis as far as the original observer O is concerned, and you're trying to see exactly what its state will look like when looked upon by another observer who is traveling along the z-axis with respect to O itself. So obviously, the particle is traveling along the z-axis with respect to this new observer with possibly a different momentum. By the way, the speed of the particle, this being a massless particle, has to be c in all frames. So the speed doesn't change, but the momentum very well can. So now, notice that under such a situation, what you have is the following. Our W, which is L inverse lambda P, lambda LP here, is a composition of three boosts. Why? This one, of course, is a boost, as we have just wrote it here. The lambda, the actual Lorentz transformation you're carrying out, is also a boost, this B of U bar. So you have B of U bar, and B inverse corresponding to the momentum lambda P, which is also in the Z direction. So this L of lambda P is also just a boost with some other parameter value along the Z direction. Now, we can of course figure out exactly what U double bar is from U and U bar, but we don't really need to do that. The basic point is this overall thing has to be some boost along the Z axis. So a structure ultimately has to be something like this. It has to have an identity along the x and y directions. And you would have gamma, gamma, beta, gamma, where beta is a corresponding overall velocity of whatever this Lorentz transformation is going to be like, whatever this boost is. But we already know what the structure of W is like. W has to be S of alpha beta r theta, and this immediately tells me from the fact that you have a 1001 here that r theta has to be rotation through a zero angle, so it has to be theta equal to 0. In fact, you can work out a bit and figure out that the only way this structure can come about from S alpha beta, r theta now of course is just identity, is that if gamma and gamma beta are 1 and 0 respectively. So that is this overall transformation, this particular little group element has to be the identity. But we don't even need alpha and beta to figure out the transformation property of the state. All we need to know is theta is 0, and that means when U of lambda acts on psi of P sigma, where P is along the z-axis and lambda is a boost along the z-axis, the overall result is simply a change which is due to this change of normalization. But other than that, this e to the I sigma theta lambda P factor here has to be just 1, theta being 0. So all that happens here is this. So for a particle which is moving along the z-axis, if you try to observe it from another observer who is also moving along the z-axis, you are actually going to end up with just an overall scale factor which essentially keeps the normalization intact, and the momentum of the particle of course is going to change according to this Lorentz transformation. So this was a rather simple case. Now let us consider another situation. Again, our initial force momentum will be mod p, 0, 0 mod p. But the Lorentz transformation that I'm going to talk about is simply a rotation rz theta. So now what is W? W is L inverse lambda p, lambda LP of course. But for this specific example, L of p will simply be B of U. Lambda is this rotation rz theta. And then L inverse lambda p, let us figure out what this is going to be. The original momentum is along the z-axis. The rotation that you're carrying out is also a rotation about the z-axis, which means the momentum does not change at all. So L inverse lambda p essentially is exactly the same as B inverse U, because lambda p is the same for momentum. The rotation about the z-axis does not change the force momentum at all. And therefore, you just have B inverse of U here. This is a similar transformation But we don't really have to calculate this out explicitly. All we notice is the following. B of u is a boost along the z-axis, so it has absolutely no effect on the x and y coordinates. It just mixes together the t and the z. Rz theta, on the other hand, leaves t and z unchanged, just mixes up x and y. In other words, these two operations actually act on an entirely different set of coordinates, so it's easy to see that they commute. And because they commute the B inverse, you can just cross Rz theta and you're left with this result. That the W, the little group element, is nothing but a rotation about the z-axis to an angle theta, and which immediately tells you that this actually corresponds to alpha equal to beta equal to 0, and theta, of course, should be the same as this angle. So when you rotate your coordinate system through an angle theta, your wave function psi p sigma changes to, so u of this particular rotation Rz theta acting on psi p sigma is actually it's the I sigma theta times psi, well, p sigma, because remember when you are rotating about the z-axis, so the forward momentum does not change at all. So all that this rotation does is gives you an extra factor of e to the I sigma theta, which is exactly what you would expect, because when you rotate about your z-axis, what comes about is the J3 eigenvalue, which is sigma. So you should really expect this. This is again essentially the same as non-relativistic quantum mechanics. What is different from non-relativistic quantum mechanics? Even in this simple situation where the momentum is along the z-axis, is if you try rotating about any other axis, not the z-axis. Now this calculation will get slightly complicated for an arbitrary axis, so let me show you two very simple cases where we are going to talk about rotations about the other orthogonal coordinate axis. This, of course, is a very special situation. I'm not talking about all possible Lorentz transformations here at all. You can, of course, carry out the calculations explicitly. That's not really too difficult. However, I want to keep things simple, so I'm going to just talk about these two special rotations. The first of these rotations that we will consider is a rotation about the y-axis through an angle alpha. So our Lorentz transformation lambda is Ry of alpha, and here we have taken alpha to be positive. Remember, an angle of rotation is considered to be positive if it is counterclockwise. So you start with an original set of coordinate axes x, y and z with the momentum, as we have said, of the particle pointing towards the z-axis. So this is our direction for p vector. We carry out a rotation about the y-axis through an angle alpha, leading to a new set of coordinate axes x prime, y prime, which of course is the same as y, and z prime. Remember, we are considering passive rotation, so it's a coordinate system which rotates around. The vector p actually has not changed, it's still the same old one, but now notice that the x prime z prime half plane, which would give us phi equal to 0 in this new coordinate system, is the one shaded green. It used to be the one outlined by blue here. Of course, it's an infinite half plane. I've just shown a section of it. The green one has become the new half plane. And that actually leads us to this conclusion. The polar angle theta is exactly equal to the angle of rotation alpha. However, the azimuthal angle phi is not 0, because in order to make this green half plane go through the vector p, you will have to rotate all the way through an angle of 180 degrees or pi. So phi is actually given by pi. So let us now use this information to try to calculate the little group element w of lambda comma p. Note that what we have at the beginning is L of p, the standard Lorentz transformation which transforms our kappa 0, 0, kappa standard forward momentum into the forward vector whose spatial part is p vector, is given by a boost along the z-axis. B of u, where u is mod of p by kappa, and this is something we have already used several times before. What is of interest is once you have carried out the rotation, which of course is a special case of a Lorentz transformation here, we now have a new 4 vector in the frame that's given by lambda p. And this new 4 vector essentially is a 3 vector which is pointing in the same old direction, but now has polar and azimuthal coordinates of alpha and pi respectively. So L of lambda p, according to our prescription, is B of u, R inverse y of alpha, and R inverse z of pi. Note that the boost is the same as before because the magnitude of the 3 momentum has not changed because of this rotation. So this B of u is exactly the same as the original B of u. Now, what about the little group element? To calculate W of lambda comma p, what we need to do is calculate L inverse lambda p times lambda times LP. L inverse lambda p, of course, is the inverse of this particular expression which I have plugged in here. Lambda is Ry of alpha, our rotation, and Lp is just B of u. Now, using standard algebra, this becomes B inverse u, then Ry of alpha, then Rz of pi, followed by Ry of alpha and B of u. Now, what we can always do is push in the identity anywhere we want. In particular, we can put in Rz inverse pi, Rz pi, which is equal to the identity between the Ry alpha and Bu here. The advantage that we gain by doing that is the following. If you take these 3 rotations one after the other, you can easily show that this is exactly the same as R inverse y of alpha, which means they will cancel out the Ry alpha. So we are finally left with B inverse u Rz pi Bu, and by the same argument that we used a while ago, Rz pi commutes with B of u, so B inverse u and B of u would cancel and you will be left with W being the same as Rz pi, and this means that our angle theta for this particular case happens to be just equal to pi. So finally, this leads to the result that when you apply a rotation of coordinates through an angle alpha, a positive angle alpha, about the y-axis, the result of that operation acting on psi p sigma is basically psi lambda p comma sigma e to the power I sigma pi. There is no overall additional factor due to normalization because lambda p of 0 and p of 0, their energy components are one and the same. That does not change under rotations. Now, while this result looks very simple at the face of it, it is really rather problematic. Note that this is actually independent of alpha. At least the factor in front, e to the I sigma pi, does not depend on alpha at all. That is, it's independent of the amount of the rotation. So it seems to imply that no matter how much you rotate about the axis y, you will get the same phase factor. While that in itself may not seem to be that much of a bad thing, but just think of what happens in the limit when alpha goes to 0. This seems to imply that even when you don't rotate at all, you are going to get an overall phase factor of e to the I sigma pi, which of course is patently absurd. Now, let me just remind you that we had made a restriction at the beginning that alpha is positive. In order to understand what's going on here, let us try to take a look at what would happen if instead of making a counterclockwise rotation through an angle alpha, I use a negative alpha. That is, I rotated through an angle modulus of alpha in the clockwise direction. So that is being depicted here. Note that under this clockwise rotation through an angle mod alpha, what will happen is that the xz plane will turn around and now x becomes x prime and z becomes z prime. Of course, y stays y prime. And now the original p happens to be in the positive x prime z prime half plane. And what that means is that while the angle theta, the polar angle, is modulus of alpha, the azimuthal angle here is just 0. So for this particular case, L of lambda p will simply be B of u multiplied by, on the left by ry inverse of mod alpha, and that's it. There is no term, no rotation about the z-axis simply because phi is 0. Now if we complete the calculation of w lambda p here, we get w lambda p equals inverse of this times ry alpha times bu. But now inverting this brings b inverse u, ry mod alpha and ry alpha, then bu. And this of course brings ry mod alpha and ry alpha together. Remember, alpha is negative, so ry mod alpha is actually a rotation ry minus alpha, which is the inverse of ry alpha. So these two things cancel each other out. And then of course b inverse u and bu cancel each other out and you are left with the identity. So for a negative alpha, the corresponding angle theta just happens to be 0. In other words, when you rotate through an angle which is negative, you carry out ry of minus mod alpha. The corresponding unitary operator u acting on psi p sigma gives you psi lambda p sigma without any phase factor. Now this looks even more complicated than before. For a positive alpha, you get a factor of e to the I sigma pi no matter what the angle alpha is. For a negative alpha, and in fact for alpha equal to 0, you get a phase factor of 1. There is no phase factor at all. Now while this may look rather complicated and unusual, it really has to do more with the way we choose our coordinate system than any special physical feature of this situation. Note that we have been using spherical polar coordinate system with the z-axis as the polar axis. And from our very first introduction to such a coordinate system, we have known that there is a problem with this particular coordinate system at theta equal to 0. That is, along the z-axis. In fact, the problem is not only at theta equal to 0, it's also at theta equal to pi, because infinitely many different values of phi, in fact any value of phi, will give you the same point when theta is either 0 or pi. In other words, the spherical polar coordinate system is singular. The coordinate system actually breaks down or becomes a bad coordinate system on the z-axis. So if we were to consider a rotation just to the right and just to the left of the z-axis, they actually end up with very different values for phi. One gives you a phi of 0, the other gives you a phi of pi. And this is really the root of the situation that we have here. This additional extra factor of e to the I sigma pi which you have for positive angles compared to no phase factor for negative angles is really due to the fact that when we defined our states, we chose an L of p and the corresponding u of L of p had these particular rotation matrices which depended on the values of phi and theta. Just think about it a bit and you will find that there is nothing really very unusual that is going on here. It's just a matter of the way in which we chose our original coordinate system and as a consequence chose the states that we considered to be psi p sigma. Let me quickly complete the discussion about special rotations by considering a rotation about the x-axis through an angle alpha. Once again, I'm going to consider the case alpha greater than 0 first. Now, when that happens, you're rotating about the x-axis. So the yz plane turns into itself. The y-axis becomes y prime, z-axis becomes z prime. And now, it's easy to see that under such a situation, the original momentum vector p now happens to correspond to theta equal to alpha, because that's the angle which it makes with the z prime axis. But phi, the angle through which the x prime z prime half plane should rotate to go through the vector p is now given by pi by 2. So L of lambda p according to our prescription is rz inverse pi by 2 ry inverse alpha bu. Carrying through with our calculation, w lambda p is the inverse of this, which becomes b inverse u ry alpha rz pi by 2, followed by the Lorentz transformation itself, namely rx alpha, followed by bu. We can insert, as before, this identity in the form of Rz inverse pi by 2 times Rz pi by 2 in between here, and that gives rise to B inverse U Rz pi by 2 Bu. Why? Because Rx pi by 2 Rx alpha, Rz pi by 2 Rx alpha Rz inverse pi by 2 happens to be Ry minus alpha or Ry inverse alpha, and that simplifies the whole calculation to give you B inverse U Rz pi by 2 Bu, which is Rz pi by 2, and hence theta for this case is pi by 2. So in this case, if you rotate about the x-axis to an angle alpha, the state psi p sigma for the new coordinate system becomes psi lambda p sigma, where lambda p of course is a rotated vector, times a phase factor of e to the I sigma pi by 2. Once again, you get a phase factor which does not depend on the angle of rotation, except for the fact that it requires the angle of rotation to be positive. If the angle of rotation were negative, what you would end up with is an extra factor, which is not e to the I sigma pi by 2, but rather e to the I sigma times 3 pi by 2. Why that is the case is something I will leave you to worry about. While I admit that the examples that we have looked at right now are rather special cases, with the intention of keeping the algebra as simple as possible, I do hope that this has given you some insight onto how states of massless particles transform under Lorentz transformations. What is actually of very much greater physical importance is the general result, namely this one. The most important point here is that the helicity, sigma, of the massless particle does not change when you apply a Lorentz transformation. So the momentum p changes to lambda p, of course. You do have an overall phase factor as well as a factor due to the normalization, but the helicity remains one and the same. So from the point of view of using Poincare transformations to classify particles, it would be natural then to say that particles with different helicities should be counted as different particles, simply because they would look like different states no matter which inertial observer is looking at it. Now, if Lorentz transformations and translations, that is Poincare transformations, had been the only symmetries that we would ever worry about, then we would have to say that all massless particles must be characterized by wave functions which have only one possible value of sigma, and therefore there would be only one state for a massless particle. But this actually runs counter to what we already know about the most famous massless particle, namely the photon. The photon is a massless particle with spin 1, and we do know that it comes in two states, which we call the two polarization states of the photon, but which really are the two helicity states. Now, the reason why the photon comes in two polarization states is that the discrete Lorentz transformation, inversion, or parity actually connects the two states with helicities +1 and -1. This is something which we have not explored so far. We are going to talk about that in the next part of this lecture course. And since parity is a symmetry of the one interaction which the photon partakes in, namely electromagnetic interaction, we do consider the two polarization states of the photon to be states of the same particle. In the very same manner, gravitons which have spin 2 and helicity +2 and -2 are considered to be two different states of the same particle, despite the fact that the helicity would be invariant under a continuous Lorentz transformation. It's parity, which is a symmetry of gravitation as well, which actually leads us to call these two gravitons two different states of the same particle rather than different particles. On the other hand, neutrinos, which we assumed to be massless until a few years ago, are particles which take part in the weak interactions which do not have parity as an intrinsic symmetry. And because of this, neutrinos with helicity +half and -half would be considered entirely different particles, neutrinos with helicity -12 are called neutrinos, and those with helicity +12 are actually antineutrinos. This distinction of treating neutrinos and antineutrinos as things with only one possible state, and photons, gravitons on the other hand as particles with two states, comes from parity symmetry of the interactions the particles partake in, not from continuous Poincare transformations. Please note that a massive spin 1 particle would actually have three different states, because each of these states would be connected to each other by Poincare transformation. On the other hand, for a massless spin 1 particle, a helicity +1 particle would stay helicity +1 forever, and a -1 helicity state would stay -1 forever under a continuous Poincare transformation. Which is what I meant when I said that these two states could have or has been seen as states of different particles. It's the parity symmetry which connects these two states to each other, which forces us to treat both of these as states of one and the same particle, namely the photon. With this, we come to the end of our rather long discussion on the way massless particle states transform under Lorentz transformations. We did mention parity transformations just a while ago. As we just mentioned, parity transformations do play a very important role, and other discrete transformations like time reversal and PT also are important issues here. These are the topics we are going to turn to in the next part of our lecture. Until then, goodbye.